In this lecture, I will talk about a newer approach to public key cryptography, which is known as elliptic curve cryptography. So, elliptic curve cryptography is known as elliptic curve cryptography because it is a public key crypto system which is based on the algebraic structure of elliptic curves over finite fields. And just like any other public key crypto system, elliptic curve cryptography also uses a hard mathematical problem or a trapdoor one-way function, which is the discrete log problem on an elliptic curve group. I will discuss this in more detail in a bit, but the main difference from previous trapdoor functions and that we have looked at is that now we are performing computations using points with x and y coordinates rather than numbers or integers. So elliptic curve cryptography is being used today primarily for digital signatures and symmetric key exchange in various protocols, including TLS, PGP, SSH, Tor, and blockchain, etc. So why is elliptic curve cryptography becoming popular? Well, because it offers performance advantages, which means that it needs fewer computations, and bandwidth advantages, which means it needs shorter keys and signatures over the traditional RSA. So we can use shorter keys and signatures to achieve the same security with less bandwidth requirement as RSA would provide with a large key. This allows small mobile devices such as IoT devices to perform complex computations and also to store keys in the small amount of storage space that they have. And the reason why we can use smaller keys in elliptic curve cryptography is because the trapdoor function in elliptic curve cryptography is stronger than the one used in RSA. So this table here shows the NIST guidelines for the required public key size to use with RSA and elliptic curve cryptography, depending on what symmetric key size is being used with advanced encryption standard. For instance, for a 128-bit symmetric key used with advanced encryption standard, the key size we would need for RSA for the public and private key should be 3072 bits. Whereas elliptic curve cryptography, public and private keys need to be 256 bits. So that's a 1 to 12 ratio in key size. That's a huge difference. Similarly, for a 192-bit AES key, we would need 7680 bits RSA, public and private key, whereas for elliptic curve, we just need 384 bits. So you can see there is a 1 to 20 ratio difference between the key size for elliptic curve cryptography versus RSA. Let's talk about the elliptic curve. So the elliptic curve cryptography uses a cubic equation such as y squared is equal to x cubed plus ax plus b. Now, depending upon what values we have for the constants a and b, we will have different equations. Let's say we have a is equal to 0 and b is equal to 1. The resulting equation would be x cubed plus 0 plus 1 or x cubed plus 1. Now, if we calculate the resulting points by choosing different values of x, which will then ultimately give us different values of y, so we will have different points that we can plot. So again, by plugging in values of x, we will have certain values of y, and then if we plot them, we will get a shape such as this. So there are several properties of elliptic curves. First, notice how it is symmetrical about the x-axis. So we have the same shape of the curve above the x-axis and the same shape below the x-axis. This is because we have a y square in the cubic equation we just saw. So for every x coordinate that you choose, we have plus y coordinate and a negative y coordinate. Secondly, any line passing through the curve intersects the curve at a maximum of 3 points. For instance, these are 3 lines, and you can see here all of them intersects at a maximum of 3 points on the curve. Another property of elliptic curve is that it contains one infinity point, referred to as capital O. It is the identity element of elliptic curve arithmetic, and we will talk a little bit more about it later. But it is technically not shown on the elliptic curve. This is a hypothetical point that we use in elliptic curve cryptography. Now, there are certain values of the constants a and b that are not allowed in elliptic curves. So these are any values of a and b that result in this equation equaling to 0. In other words, a and b values should be chosen such that 4a³ plus 27b squared when computed is not equal to 0. Otherwise, it results in an elliptic curve with singularities, or causing either what is known as a cusp and a self-intersection. For example, the left curve right here has a is equal to 0 and b is equal to 0. That's why we have y squared is equal to x³ as the resulting equation. So if you plug in a is equal to 0 and b is equal to 0 into this equation, you will see that it gives you 0. Similarly, the right curve right here has a is equal to -3 and b is equal to 2. Again, if you plug in a is equal to -3 and b is equal to 2 into this equation, you will see that it results in a 0. So this curve right here has a self-intersection. So this is again a singularity which is not allowed. Similarly, we have this first graph which is a cusp, which means that it meets itself at a point. So this is also not allowed. And we cannot use an elliptic curve with singularities because it causes issues with point addition arithmetic, which I will discuss in a bit. So here are some examples of valid elliptic curve. And although the shape of this left curve right here with a is equal to -1 and b is equal to 0 looks different from the curve here on the right, which has a is equal to -1 and b is equal to 1. It is still a valid curve because it satisfies all the properties that we just talked about. For instance, it is symmetric about x-axis. Also, if you draw a line through the curve, it will intersect it at a maximum of 3 points. And here are the resulting equations which we get with a is equal to -1 and b is equal to 0, and with a is equal to -1 and b is equal to 1. So pause here and find out if y squared is equal to x³ plus 1x plus 0 is a valid elliptic curve. So the answer is that it is a valid elliptic curve because here we have a is equal to 1 and b is equal to 0. So if we plug in this value of a and b into this equation right here, it will not result in a 0. This means that we can use this cubic equation. Now pause here and use this calculator at this link to explore elliptic curves for various values of the constants a and b and notice their properties. So if you open this link, you'll get something like this. So if I change the values of b or a, you will see that I get different shapes of my resulting elliptic curve. And also you can see here that I can choose point a and b, one shown in orange and one shown in blue. If I select any 2 points, you can see here a line is drawn through those points and it intersects it at a maximum of 3 points. So I can change where this line is, and wherever this line is, you can see here it intersects a graph at a maximum of 3 points. So that's a general overview of elliptic curves. However, we don't use them as is for cryptography purposes. We define what is known as an elliptic curve over finite field. This is because we always use finite fields in cryptography. So we define an elliptic curve over a finite field using a prime number. This is also represented as fp, where p is the prime number. So an elliptic curve over finite field, as the name says, consists of a finite set of elements, in this case points with x and y coordinates. Each point's x and y coordinate, however, is supposed to be greater and equal to 0 and less than p, which is our prime number. So we only work with positive integers that are less than the chosen prime number of this finite field. So which points to include in this finite field? These are all the points that satisfy the following cubic equation. We have y squared mod p is equal to x³ plus ax plus b mod p. So the only change that we have made now is the addition of this mod p. because we're working with finite fields, so we want to make sure that all the x and y coordinates we have are less than the prime number. Now all the computations we will do will be on these points in the finite field, and the result of these computations will also be one of the elements in this finite field. Let's take a look at an example to understand this better. Let's say we want to calculate elliptic curve over the finite field for prime number 5. So we can denote this as f5. Let's say a is equal to 1 and b is equal to 1 as well as our constants. So our resultant cubic equation for our elliptic curve will be y square mod 5 is equal to x cubed plus x plus 1 mod 5. So this is our a value and this is our b value. So now the possible x coordinates are 0, 1, 2, 3, and 4. So we include 0 as a possible coordinate, and the highest coordinate that we can have is less than our prime number, so which is 4 in this case. Similarly, our possible y coordinates are also 0, 1, 2, 3, and 4. Now we need to find out which combinations of these x and y coordinates are valid points on this elliptic curve over finite field. To do this, we will plug them in this equation and see if the left hand side is equal to the right hand side. So let's say we plug in x is equal to 0 and y is equal to 0 into this equation. The resulting value on the left side should be equal to the resultant value on the right side. So we have to try all possible combinations of these x and y coordinates. So for example, we can have 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. Similarly, we can have 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, and so on. But not all of them might be valid points on this elliptic curve over finite field, f5. So we have to find all the valid points that form this finite field by plugging them into this equation and checking which ones give us left hand side equal to right hand side. So if you try that out, you'll see that the total number of valid points for this specific equation come out to be these 8 points. We have 0, 1, 0, 4, 2, 1, 2, 4, 3, 1, 3, 4, and 4, 2, and 4, 3. These are 8 points, and the total number of points in our finite fields then is 8 plus 1. There's always the infinity point that we include in our finite fields in elliptic curve cryptography. So in other words, total points that we have in f5 is equal to 9, which are all these plus the infinity point. So let's verify that 0, 1 is a valid point by plugging it into this equation right here. So here we have x is equal to 0. If you calculate the right hand side, we get 0 cubed plus 0 plus 1 mod 5, which basically is 1 mod 5, which is equal to 1. So right hand side is equal to 1. And then our y coordinate here is equal to 1. So we plug it in on the left hand side, we get 1 square mod 5, which is also 1 mod 5 or 1. So this means right hand side is equal to the left hand side, which means this is a valid point. And again, you cannot see some points in this list. For example, 1, 1 is not a valid. So why is it not a valid point? Because if I plug in x is equal to 1 on this side, we get 1 plus 1 plus 1 mod 5, which is 3 mod 5 or 3. And then if I plug in y is equal to 1 on the left hand side, I get y square mod 5, which is equal to 1. So 1 is not equal to 3. This means left hand side is not equal to right hand side. So this is not a valid point. And so if you plot all these 8 points, we get something like this. This is actually our elliptic curve over the finite field f5. And again, you will not see the infinity point because we don't really represent the infinity point visually. So you can use the visualizer at this link right here to calculate the elliptic curve over finite field. To do that, you have to provide the values of A, B, and P. Okay, so this figure right here is showing you the points in f5 using this equation through this calculator. So pause here and calculate the elliptic curve over the finite field f17 using this cubic equation. You can again use the visualizer at this link to verify your answers, as it also calculates the finite field for you. So this is the finite field that you get from this cubic equation. So it has a total of 18 points that you see plotted in this figure. So this is the finite field. So let's actually try using this elliptic curve finite field visualizer to see how we get this graph right here. So to use this calculator, you have to provide it the values of a, b, and p. Here r is the prime number. So in this exercise, we have a is equal to 0 and our b value is 7 and our prime number is 17. So after plugging in these values, we click draw, and this shows us the resultant finite field. So again, we have 18 points here, which is also including the infinity point. So technically, the plotted points are only 17 points, and the 18th point is the infinity point. Let's look at some important parameters for elliptic curves over finite field. So we just looked at the first three of these. So P is the prime number for the finite field, A and B are the constant values on the curve equation. Then we have a generator or the base point G. This is one of the valid points in the finite field. It is usually either the smallest point, or it can also be a random point selected from this finite field, which is used in the public key generation, symmetric key exchange, and digital signature. The parameter n determines the maximum number that can be used as an elliptic curve private key. Any number in the range of 1 and n-1 is a valid private key. And so this is also the smallest positive integer, which when multiplied with the generator point results in the infinity point, or the identity element that we have as part of our finite field. So we will discuss this in a bit when we get to point addition. H is the number of valid points on the elliptic curve divided by n. So usually it has a constant value of 1 because the number of valid points on the elliptic curve and the value of n are typically going to be the same. So when you divide them, you get 1. Let's take a look at these parameters in this elliptic curve. So here the prime number is 17, A value is 2, and B value is 2. And if you calculate the total number of valid points in this field using the calculator I just showed you, you will see that there are 19 points in this finite field, which also includes the infinity point. And let's say our generator point is 5,1. So our G value is 5,1. So let's find the values of n and h. So then let's find the values of parameters n and h. To find n, we will compute 1g, 2g, 3g, 4g until we get a number which when multiplied with g gives us the infinity point. So if you try this out, you will see that when you do 19g, the resultant value is infinity. This means our n value is equal to 19. So this is the smallest number which when multiplied by the generator point gives us the infinity point. And so our h parameter then is 1 because we get it by dividing the number of points in our finite field, which is 19, by n, which is also 19. So this gives us 1. So this figure shows the resulting points when performing 2g, 3g, all the way up to 19g. So notice that for 19g, we are getting the infinity point. So I will be discussing what 2g, 3g, 4g, etc. computation means in a bit, and how did we get these resultant points. So pause here and use Google to find the following parameters for P-256, which is an elliptic curve over finite field in use today. It is also known as sec P256R1 and prime 256V1. So these are all different names for the same elliptic curve. So just Google it and find out the values of all these parameters. So here are the parameters for P-256 or sec P256R1 elliptic curve. Now these are represented in hexadecimal, but if you convert them to decimal, you will notice that the prime number is a very large value, so that we have sufficient number of valid points in the finite field to keep the trapdoor function secure against attacks. And notice here that h has the value 1, just like we saw in the previous example, and g over here is a point. As you can see over here, we have comma to separate the x coordinate and the y coordinate. And these are the values of our constants a and b, and this is our n value. You can look at these values using this link right here. This figure shows the commonly used elliptic curves today. So P-256 is the most used, 74%, followed by X25519, which has 22% usage. This one is mostly used for elliptic curve Diffie-Hellman key exchange. And then we also have some other ones, such as P-521 and P-384. You can check this reference right here to find parameters for other NIST recommended elliptic curves. Let's talk about how to add 2 points on elliptic curves in general. Then we will see how to do that on elliptic curves over finite fields. To add 2 points P and Q on an elliptic curve, we draw a line passing through these points P and Q. This line will then intersect the curve on a third point, R. So the result of P plus Q, or the addition of P and Q, is the inverse of point R. In other words, it's the reflection of point R, taken as x, minus y. So, for instance, if we want to add points P and Q on this curve right here, we're going to draw a line through these 2 points, P and Q. As you can see here, this line intersects the curve at a third point, R. So, the result of addition of points P and Q is actually the reflection of this R point, or its inverse. So its reflection is this point right here, which is the same x coordinate, but minus y. Here is another example. Let's say now we want to add these 2 points, P and Q. Okay, so we draw a line through these 2 points, and you can see here that this line intersects this curve at another point. So the reflection of this third point is actually the result of addition of points P and Q. So what will be the reflection of this point? It's going to be the same x coordinate and inverse of the y coordinate that we have for this point. So in this case, we already have a negative y. So over here, the reflection point will have a positive y coordinate. In the first example, we have a positive y coordinate for r. So for r's reflection, we will have a negative y coordinate. However, in elliptic curve cryptography, we work with finite fields consisting of positive integers. So there are no negative coordinates. Therefore, we use these formulas to add the 2 points in elliptic curve over finite field. So x3, y3 is the resultant point from the addition of point P, which is x1, y1, and point Q, which is x2, y2. So x3, y3 can be thought of as the reflection of the third intersecting point on the curve when we draw a line through points P and Q. Now, how do we get x3, y3? Well, first we calculate the slope s of the line passing through the points P and Q. Now, there are 2 scenarios here. One is when the 2 points that we're adding are different, which means point P is different from point Q. So we use this formula right here, which is y2 minus y1 divided by x2 minus x1 mod P to calculate the slope. This scenario is known as point addition. The other scenario is when the 2 points that we want to add are the same. So technically you're adding the same point to itself. In other words, P plus P or Q plus Q. This scenario is known as point doubling. In this case, we use a different formula for calculating the slope, and this formula is 3x1 squared plus a divided by 2y1 mod p. This is because using the first formula in this scenario will result in infinity, since x2 minus x1 will give us 0 because x2 and y1 are the same value. So our denominator will become 0. So anything divided by denominator is infinity. And so once we have the value of s from either of these 2 equations, then we plug that value s into this formula right here along with x1 and y1 values to get x3 coordinate, and then we plug in our s value along with x3 value that we just got and x1 and y1 value in this equation to get y3 coordinate. and then we have our resultant point x3, y3. So let's look at an example. Let's say we want to add points P and Q given this elliptic curve over finite field. So our points are 5, 1 and 6, 3, both of which are part of this finite field. Now the first step is to find the slope S. Now since these points are not equal, we are going to use this first formula right here. So plugging in the values in this formula right here will give us S is equal to 2. So y2 over here is 3, y1 is 1, so we have 3 minus 1, and then x2 is 6, and x1 is 5, right? So we get 2 by 1 mod 17, which is basically 2. Now once we have S, we will plug it in these formulas to get our resultant point. First, we will get x3. So x3 is equal to 10. We will then find y3 using this formula. This will give us 6. So our resultant point from adding P and Q is 10, 6. Let's verify it using this elliptic curve point addition calculator at this link. So in order to use this calculator to add points, first we have to actually calculate the finite field. And to do that, again, we are going to plug in the values of A, B, and P. So A in this case is 2 and B is also 2. And the prime number we have is 17. So I'm going to click draw here. This is going to give us the elliptic curve over finite field for prime number 17 given this A and B value. Now, how do we add points 5, 1 and 6, 3? First, notice that 5, 1 is this point right here, and 6, 3 is this point right here. So these are two valid points in this finite field. So we have to add these points. To add these points, we can actually use this table of point additions right here. And to use this table is pretty simple. All you have to do is just look at the row and column label and pick the value at their intersection. So these numbers in red are the labels which have the point values that you would want to add. So if I want to add 5, 1 and 6, 3, I could, let's say, use 5, 1 from here as this row label, 5, 1, and then 6, 3 I could choose as this column. So one point has to be the column label and one point has to be the row label. Which point you use for the row label and which point you use for the column label is completely up to you, because P plus Q is going to be the same as Q plus P. So it doesn't matter if you add 5, 1 plus 6, 3 or you add 6, 3 plus 5, 1. It's still going to give you the same resultant points. So 5, 1 and 6, 3 gives us 10, 6. Right, so again, if I do actually 6, 3 like this as the row label and then look at column 5, 1 right here, it's still going to give me 10, 6. 5, 1 and 6, 3, still 10, 6. Right, so we get the same value using this calculator as well. So now pause here and add the points P is equal to 5, 1 and Q is equal to 5, 1 using this elliptic curve over finite field and these formulas. And you can again also use the point addition calculator at this link to verify your answer. So now we have a scenario where the 2 points to be added are the same, which is 5, 1. So this is a point doubling scenario, right? I can also write this as either P plus P or Q plus Q, right? So this would be doing 2P, this would be doing 2Q, since we're referring to the same point. Now, this means that to find the slope, we're going to use this second formula right here. So we'll plug the values in this equation, but you'll notice that after plugging in the values, we get 77 by 2 mod 17, which actually will not result in a whole number, but we can only have whole numbers through our computations in elliptic curve cryptography. So what we'll do instead is that we will write 77 by 2 as 77 into 2 raised to power minus 1, right? So 1 by 2 can also be written as 2 raised to power minus 1. And further, I can actually perform this computation as 77 mod 17 into 2 raised to power minus 1 mod 17. So 77 mod 17 is pretty simple. That will give us 9. But how do we calculate 2 raised to the power minus 1 mod 17? For this, we can use the modular multiplicative inverse calculator that I've provided here at this link. You provide the number whose modular multiplicative inverse you have to find. So in this case, we're trying to do it for 2, and then our prime number, which is 17. So we're doing 2 inverse modulo 17. So this gives us 9. So as you can see over here, we get 9. However, 9 into 9 gives us 81, which is a number larger than the numbers that we have in our finite field. However, 9 into 9 gives us 81, which is larger than the prime number. So we will again reduce it by doing modulo 17, right? So 9 into 9 mod 17 gives us 13, which is less than the prime number, so we can use it. So our S value is 13. Now we will plug in the value of S into these formulas to get our coordinates x3 and y3. So x3 comes out to be 6 and y3 comes out to be 3. This means our resultant point is 6, 3. 5 plus 1 plus 5 plus 1 gives us 6, 3. Let's verify 5, 1 plus 5, 1 is equal to 6, 3 using this calculator as well. So now here I have calculated the finite field. Now I'm going to go to the table of point additions and add 5, 1 and 5, 1. So I'll choose the row which has 5, 1 as the label, and then I'll also choose the column which has 5, 1 as the label. So you can see over here, I selected the row which has 5, 1 label, and I selected the column which has 5, 1 label. So its intersection is the point 6, 3. Okay, so now that we know how the point addition works in elliptic curve cryptography, let's understand the trapdoor function in elliptic curve cryptography as it leverages this concept. So the trapdoor function here says that if we calculate the point capital A by multiplying small a and capital G, where capital G is a point on the elliptic curve over a finite field. This is also the generator point, and small a is a random number that is kept secret. So how do we calculate this capital A point? We get it by computing several point additions. So we add the point G A times. So we do G plus G and then add the result again to G, then again add that result to G, and we do that A times. This is the same as multiplying A with the G point. Now the idea is that if I have capital A equal to small a times capital G, reversing this resultant point capital A to get the secret number small a given this generator point capital G is supposed to be computationally hard. And this is referred to as the discrete log problem on elliptic curves. How to find small a given capital G as well as capital A. So for instance, let's say our capital G is the point 2, 3, and let's say we choose a secret number equal to 5. So capital A will be computed using the computation small a times G, which is equal to 5 times 2, 3. So if you're wondering why can't we just do 5 times 2 and 5 times 3 to get something like 10, 15, isn't that a times G? No, that's not how we perform this computation in elliptic curve cryptography. So the way we perform this computation is through several point additions. So 5 times 2, 3 can be broken down into adding 2, 3 point 5 times. So I can break this down into smaller addition problems. So let's assume 2, 3 plus 2, 3 on this elliptic curve gives us 5, 9. This is also going to be 5, 9. So now I have to add 5, 9, 5, 9, and 2, 3. So let's assume 5, 9 and 5, 9 when added gives us 1, 2. Then if I add 2, 3 to this, let's assume this gives us 4, 5. So capital A will be 4, 5. Now the idea is that if I give you 4, 5 and I give you 2, 3, finding out the value of small a, which is 5, is supposed to be computationally hard. Because now you have to try out various numbers with the point G to find out which of them gives you the resulting point as 4, 5. So now let's look at how to generate public and private keys in elliptic curve cryptography. In elliptic curve cryptography, the private key is always a number. It's a large random number that is less than the parameter n that we talked about a few moments ago. So the private key is supposed to be kept private, just like in RSA. It's any random number that is less than the parameter n. The public key in elliptic curve cryptography, however, is a point and not a number. It is a point resulting from performing this computation A times G, where G is the generator point. And like we just saw, we compute A times G by turning this into a point addition problem, right? So we do G plus G A times. So we add the point G A times. So let's say we have the generator point as 5, 1 on an elliptic curve. And let's say performing 9 times G gives us 7, 6. So in this case, 9 will be our private key, which is how many times we are adding the G point to itself. And the resulting point that we get from performing 9G, which is 7, 6 here, is our public key. So let's say we have the generator point equal to 5, 1 on an elliptic curve. And let's say we are performing 9G, which gives us the point 7, 6. So in this case, our private key is the number 9, which is how many times we added the G point to itself. And our public key is 7, 6, which is the result from performing the computation 9G. So take a moment here to think about all the possible private keys we can use given the following elliptic curve parameters. So the answer is that since a private key is any number between 1 and the parameter n, so in this case, since we have n is equal to 26, we can have our private key as any of these values. So we can have private key equal to 2, 3, 4, 5, all the way up to and including 25. Now let's say the private key is 8, then what would be the public key given the following elliptic curve parameters? You can use the calculator at this link to compute the answer. So here you have to perform 8 times G, where G is 4, 9. So you have to perform 8G, which is 8 into 4, 9. The result of this will be a point, which will be your public key. So pause here and calculate this point. So to do that, you can break down 8G into smaller problems. So we can say we are adding 4, 9 8 times. So that's 8 times. So let's compute 4, 9 plus 4, 9. So we'll just replace all of these with the same point. So we can use this calculator again. So now we have to choose the right values. In this case, A is 3 and B is 5. And prime number is 19. So this is the resulting elliptic curve over finite field that we have. And now let's use this table of point additions to add 4, 9 to 4, 9. So 4, 9, let's choose this row, which has label 4, 9, and again choose this column, which has label 4, 9. So we get 9, 18, which is the result of adding 4, 9 to itself. Okay, so we're gonna write 9, 18 here. This is 9, 18, this is 9, 18, and this is 9, 18, and 9, 18. Now we're going to add these points. So let's add 9, 18 to itself, and then we're going to replace this one as well with the same answer. Let's go back here. So now I'm going to choose the row labeled 9, 18, and the column labeled 9, 18. We get 6, 12. So this will be 6, 12, and this is also 6, 12. So the last step is to add 6, 12 to 6, 12. So I'm going to choose the row label 6, 12 as well as the column label 6, 12, which gives us 18, 18. So basically 8G is equal to 18, 18. So OpenSSL supports elliptic curve key pair generation. You can use the following command to specify an elliptic curve and generate your key pair, which is both the public key and the private key. Now this will generate a base64 encoded file. So if you want to read the values of your public and private keys, you can use this command to decode the base64 encoded file and display the values in a readable format. So this is how your base64 encoded file will look like, and this is how this command will display your public and private keys. You can see your private key and public key both are 256 bits, since we're using an elliptic curve that generates 256-bit keys. And the values shown over here for public and private keys are in hexadecimal. And also notice that private key here is a number, and the public key, however, you can see here the size is larger because it's a point, not a number. So in this case, we have a 256-bit x coordinate and a 256-bit y coordinate. So here, the first half is an x coordinate, the next half is a y coordinate. And we ignore this first byte. The first byte value in this public key shows how the public key point is represented. So 04 here means that both x and y coordinates are shown concatenated. If, however, the value of this first byte is not 04, this means that only the x coordinate is displayed, mostly to save the space. And the y coordinate can be calculated by plugging in this x coordinate into the elliptic curve equation. You can also export the public key from this key pair into a separate file to be able to share it publicly with others. So here is the command that you can use to do that. Again, this will generate a base64 encoded file, which will look something like this. And so if you want to see the contents in a readable format, you can use this command, and that is going to display the value of the public key like this. And you can also again see which curve is used to calculate this public key. So here is an example of a website that uses elliptic curve public key. So this is Google's 256-bit elliptic curve key that is created using the P-256 elliptic curve. So this public key is taken from Google's digital certificate via the Firefox browser. And there are, of course, many other websites that use elliptic curve keys. This is just one example. So all we see over here is the public point, because the public key is essentially a point. And so this is again a concatenation of the x coordinate and y coordinate. So first half of this large value is the x coordinate, and the second half is the y coordinate. And the reason for that is because the first byte over here says 04, which means that both x and y coordinate are represented here in concatenated format. Since elliptic curve cryptography is also used for symmetric key exchange, so there is an elliptic curve version of Diffie-Hellman key exchange. This figure shows the steps involved in elliptic curve Diffie-Hellman key exchange. And the main idea is similar to that in the non-elliptic curve version, in that both sides agree on some public parameters, and then they select their private keys and compute the corresponding public keys. Then they exchange these public keys and use the other side's public key to mix it with their own private key to get the shared key. So again, both sides end up with the same key instead of actually sharing the secret key, since all exchange is done in plain text. So in this case, the shared parameters is information about the elliptic curve and its parameters. For example, the parameter n and the generator point g. So Alice and Bob will both pick a random number that is going to be less than n, and they will keep this number secret, since this forms their private key. So private key is any number that is greater than 1 and less than the parameter n. So in this case, for Alice, we have private key dA, and for Bob, we have private key dB. Each side will then compute their public key as private key times the generator point. So Alice will compute QA as their public key by doing dA times G, and Bob will compute QB, which is their public key, using dB times G. So these computations will be done by converting this multiplication problem into a point addition problem. So essentially, Alice is going to add the G point dA times, and Bob is going to add the G point dB times. So the next step would be then to exchange their public keys. So Alice will send QA to Bob, and Bob will send QB to Alice. So now Alice will calculate the shared key by mixing her private key with Bob's public key. So Alice will do dA times QB. Again, over here, dA is a number, QB is a point. So this can be turned into a point addition problem by adding the point QB dA times. Similarly, Bob will multiply his private key, which is DB, with Alice's public key, which is QA. And again, this can be converted into a point addition problem by adding the point QA DB times. And so notice that this shared key over here is essentially a shared point and not a number. So this can be transformed into a key. So how do we convert this shared point into a key that can, for instance, be used as the session key? So first we calculate the hash value by concatenating the x and y coordinates and passing that value through the hash function. Then we discard the extra bits of the hash value depending on the required key length. So in a 256-bit elliptic curve cryptography scheme, hashing the x coordinate or both x and y coordinates using SHA-256 hash function will result in a 256-bit output. And so if we're using AES-128, we just need the first 128 bits from that hash value and we will discard the remaining ones. If, however, we are using a 256-bit key with advanced encryption standard, then we will not be discarding any bits. So let's assume that Alice and Bob have agreed on an elliptic curve to use. So they both have, let's say, a G point and they both have an N value, as well as, of course, the elliptic curve. Now they both will pick their private keys. So let's say Alice picks 2 and Bob picks 5. And the idea here is that these numbers are less than this parameter N. The next step then is for both of them to compute their public key. So Alice will compute her public key by multiplying the private key with the generator point. So let's assume the generator point here is 5, 1. So Alice will multiply 2 with 5, 1, and let's assume that gives us 6, 3. And then Bob is also going to do the same computation. So they're going to multiply their private key with the generator point 5, 1. And let's say they get a point 9, 16, which is their public key. So they are then going to exchange their public keys. This means 6, 3, which is Alice's public key, is going to come to Bob, and 9, 16, which is Bob's public key, is going to come to Alice. And so finally, they're going to then mix the received public key with their own private key. So Alice is going to multiply her private key with Bob's public key. So 2 times 9, 16, which is, let's say, going to result in 7, 11. And then Bob is then going to multiply their private key, which is 5, with the received public key, which is Alice's public key 6, 3. So they will get a point from this computation, which is, let's assume, going to be 7, 11. So now Alice and Bob have both computed the same point, which is 7, 11. This is a shared point. And then they can convert this point 7, 11 into a key that can be used as the session key. So pause here and perform Diffie-Hellman key exchange using the following elliptic curve parameters. You can use the following calculator to perform the point additions. So in this case, we have n is equal to 19 and our generator point is 5, 1. And so let's say Alice has chosen 3 as the private key and Bob has chosen 5 as their private key. This means Alice is going to calculate their public key as 3 times 5, 1, and Bob is going to calculate their public key as 5 times 5, 1. So let's use this calculator to perform 3 times 5, 1 and 5 times 5, 1. So 3 times 5, 1 would be adding 5, 1 3 times. So let's choose the row labeled 5, 1 and the column labeled 5, 1. So we get 6, 3, which is 5, 1 plus 5, 1. So let's add 6, 3 again to 5, 1. That will give us 3 times 5, 1. So again, I'm going to keep the row label as 5, 1, and now for the column label, I'm going to choose 6, 3. So that gives me 10, 6. So this is actually equal to 10, 6. And so to calculate 5 times 5, 1, I'm just going to add 5, 1 and 5, 1 to 10, 6. So this is essentially equal to 10, 6 plus 5, 1 plus 5, 1. Or in other words, this is equal to 3 times G plus G plus G. 3 times G we have already computed. And then we just saw that 5, 1 plus 5, 1 was 6, 3. So I'm going to add 6, 3 to 10, 6 to find 5 times 5, 1. So let's choose the row labeled 6, 3 and column labeled 10, 6. So we get 9, 16. So 5 times 5, 1 is equal to 9, 16. So public key of Bob is 9, 16, and public key of Alice is 10, 6. So now they both will exchange the public keys. So 9, 16 is going to come here, and 10, 6 is going to go here. So now Alice is going to compute 3 times 9, 16, and Bob is going to compute 5 times 10, 6. So let's compute 9, 16 plus 9, 16 plus 9, 16 first. So I'm going to choose the row labeled 9, 16 as well as the column labeled 9, 16. That gives us 7, 11. Let's again add 7, 11 to 9, 16. So again, I'm going to keep row labeled 9, 16 and column labeled 7, 11 this time. So this gives us 3, 16. So 3 times 9, 16 is 3, 16. Let's now compute 5 multiplied by 10, 6. So to calculate 5 times 10, 6, I can first find out what is 10, 6 plus 10, 6. And then I can take that result and add it to itself. That will give me 4 times 10, 6. And then I can just add 10, 6 again to that result. That is going to give us 5 times 10, 6. Let's see what 10, 6 times 10, 6 is. So to do that, I'm going to choose a row that's labeled 10, 6 as well as a column that's labeled 10, 6. This gives us 16, 13. So to do 4 times 10, 6, I'm just going to add 16, 13 to 16, 13. So choose a row labeled 16, 13 and a column labeled 16, 13 gives us 0, 11. So finally, I'm going to add 10, 6 to 0, 11. Let's choose a row labeled 0, 11 and column labeled 10, 6. This gives us 3, 16. So 5 times 10, 6 is also 3, 16. So what we did to do this computation was we did 10, 6 plus 10, 6 plus 10, 6 plus 10, 6 plus 10, 6. That's 10, 6 added 5 times. And then first, if you remember, we got 16, 13. So I just replaced this one as well with 16, 13. And this one added together gave us 0, 11. Then when I added this again to 10, 6, this gave us 3, 16. Okay, so our shared point in this case is 3, 16. And we can convert this to a symmetric key. Just like we have an elliptic curve version of Diffie-Hellman key exchange, similarly, we also have an elliptic curve version of digital signature algorithm. Again, the main idea is same in that we use the private key of the sender to create the digital signature on a hash value of the message. Similarly, for verification of the signature, we need the sender or the signer's public key. Again, just like the non-elliptic curve version of DSA, we have a per signature random number, which is used only at the sender side's computations, or in other words, during the signature creation. There's also a set of shared public parameters, which consist of an elliptic curve, and again, the prime number, the generator point, and the n parameter. And these are used both at the sender side as well as at the verifier or the receiver side. The digital signature comprises of 2 values, R and S, and the verification function takes as input the hash value of the message, the signature components R and S, the shared public parameters, as well as the sender's public key. And the value x1 is then computed through this verification function, and if this value is equal to the R value in the digital signature, then our signature is verified, or in other words, the user or the message is authenticated. Now you can visit this link right here to look at the elliptic curve digital signature algorithm in detail and the exact computations that are done in the signature creation function as well as the verification function. Just like RSA and DSA, OpenSSL also supports elliptic curve digital signature algorithm. So here are the commands that you can try out to create and verify the elliptic curve digital signature, in this case using SHA-1 as the hash function.